Let's move to question number 11 now. A meter stick is balanced on a knife edge at its center. When two coins, each of mass 5 grams, are put one on top of the other at the 12 centimeter mark, the stick is found to be balanced at 45 centimeters. What is the mass of the meter stick? Initially, a meter stick is balanced on a knife edge at its center. Okay, so I have a meter stick here. Look at this. This is the meter stick. It is balanced at the middle point. Okay, the meter stick is balanced at the center like this, right at the center. All right, it is balanced because this is a uniform mass distribution. The scale has same mass all along. So the center of mass is right at the center and it will be perfectly balanced. Now let us go on reading. When two coins, each of mass 5 grams, are put one on top of the other at 12 centimeter mark, look at that. You're going to put two coins where at 12 centimeter mark. Somewhere here, you're going to put two masses like this, two coins. Then obviously, this will tilt down. Okay, because the balance is gone, this will tilt down. So you have to push this to the left so that it stays balanced again. Okay, so you have put two masses here, small masses, they are two coins, and the center of mass has shifted now. You need to move the wedge to another location so that it stays horizontal again. So let's see where the point is. When two coins, each of mass 5 grams, are put on top of the other at the 12 centimeter mark. So let us draw it. See this? I'll draw the second configuration now. We have the same scale, meter scale, right? The meter scale, same meter scale. All right. But this time around, you're going to put two small masses, two small coins, 5 grams each. Where are they put? At like 12 centimeter height, 12 centimeter distance. Okay, one coin like that, another coin like this. All right. So two coins are put at 12 centimeter mark. This is like, this location is like 12 centimeters. Okay, 12 centimeters from the left end. Now, the stick is found to be balanced at 45 centimeters. Now, the wedge has to be placed where? Not at the geometric center anymore, but at 45 centimeters. Look at that, 45 centimeters. You are placing it at 45 centimeters. Okay, what is the mass of the meter stick? All right, so let us mark the distances. The distance to the coin here is 12 centimeters. Okay, the new location of the wedge is 45 centimeters, which means this distance must be 33 centimeters. Why? Because total distance is 45. The distance from the edge to the coins is 12. And coins to the new position of wedges, 33. Sorry, new position of wedges, 45 minus 12. That is 33. All right. So this is the new configuration now. And let us look at the torques here. The system stays horizontal means this is in equilibrium. All right. So let us put the condition for equilibrium. We will see rotational equilibrium because it has a tendency to rotate. So I'll take what? I'll take, if it stays in equilibrium, the torque has to be equal to 0. Torque has to be equal to 0. What are the torques created here? One torque is created by the weight of the body. Weight of the meter stick is acting through what? Weight of the meter stick is acting through the center of mass of the scale. Original center of mass of the scale. That weight is how much? Weight is equal to mg. All right, mg. And let us see the couples now. Let us see the torques now. There are two torques. One torque created by the weight of the scale. Another torque created by the weight of the coins. Weight of the coins. Let's draw that as well. Weight of the coins. That's creating a torque this way. Look at that. Look at that. It's acting straight downward. Okay. So see this. All right. So there are two weights. This weight is how much? 5 grams. So 5 grams into G. This is 5 into G. This weight is 5 into G. I'll keep it in grams itself. Okay. This G is not gram. It is 9.8 meter per second square. Mass into G. Weight is equal to mass into G. Now, what is the condition for equilibrium? We need the total torque to be equal to 0. Sum of all torques should be equal to 0. There are two torques created. Look at this. As it is held this way, this weight is pulling it down, which means it is in clockwise direction. This torque is in clockwise direction, whereas this weight is pulling it down this way, which is anti-clockwise direction. So the torque created by, couple created by the weight of the scale is in clockwise direction, whereas the one created by the coin's weight is in anti-clockwise direction. So we write the torques one by one. Remember, anti-clockwise torque is taken positive, clockwise torque is taken negative. Okay, so let's write the anti-clockwise torque. How to write the torque? Torque is given by force into perpendicular distance. Force, this is force, 5G. 5G into perpendicular distance to the axis of rotation. This is the point of rotation. We are finding the torques about this point. You can find the torque about any point. So, force into perpendicular distance. Force into perpendicular distance. The force here is nothing but the weight. Weight is 5G into perpendicular distances 33, which is anti-clockwise torque. So I should put it as positive. Plus the torque given by the weight of the scale, which is mg into the distance to this point. Original center of mass was at 50, right? This distance is 50 because for the original scale, center of mass is at 50. And this point is 45. Correct. The wedge is now located at 45. Original center of mass of the scale was 40. So that distance must be how much? That distance must be 5 centimeters. So you're finding the torque about this point. Torque by the weight of the coins is force into distance. 5G into 33. 5G into 33. Now, torque due to the weight of the scale is mg into 5. The distance to the point of rotation is 5. mg into 5. But see this? That is equal to 0. But there is one thing. This torque is clockwise torque. Clockwise torque. Clockwise torque should be given negative sign. So let's get to the right hand side. 5G into 33 should be equal to, this goes to the right side, 5 mg. Let's cut the common terms out. G and G are cut. 5 and 5 are cut. And mass of the meter scale is 33 grams. Oh, I made a small mistake. There are two coins, no? Each with 5 grams. All right. So I should have put 5 plus 5, 10 grams there. I'm sorry. There are two coins, each one having mass 5 grams. So that should be 10G. So I should make the corrections here. This should be 10G. This should be 10G. This should be 10G. All right. And 10 and 5 are cut with 2. All right. G and G are cut. And finally, you are left with M is equal to 2 into 33. That is equal to 66 grams. That is the mass of the meter scale. This is question number 11. All of you understood?